Hello, everybody. Welcome to our panel, Network Security from PAN to WAN. Although we're going to WAN to PAN, we're starting big with the WAN, and we end with the near-field communications. Wireless networks have become an integral part of modern society, facilitating seamless communications and connectivity. They encompass a variety of technologies, including wide area networks, 5G, and short-distance protocols, each serving distant yet complementary purposes. Wide area networks enable connectivity over large geographical areas, allowing businesses to connect offices across cities, countries, or even continents. This connectivity supports global commerce, remote work, and international collaboration, making WAN essential for functioning of the modern economy. 5G technology represents the latest advancement in cellular networks, offering significantly faster speeds, lower latency, and the ability to connect a vast number of devices. 5G is set to revolutionize various sectors, from healthcare with remote surgeries, telemedicine, to transportation with autonomous vehicles and smart cities. 5G is a commercial standard and therefore doesn't comply with military-grade networks. But since it offers added value in the sense of speed, availability, and certainly cost, the question arises if the use of 5G potentially with adaptations for some military scenarios is possible. And then Bluetooth, Zigbee, RFID, and many other protocols are pivotal for short-range communications. It's widely used in personal devices such as headphones, fitness trackers, and smart home applications. The ease of connectivity enhances user experience and supports a wide range of applications in everyday life. One has to consider the cybersecurity aspects of those protocols, and others are depending on the use case. So in conclusion, wireless networks are a cornerstone of modern military infrastructure. The importance cannot be overstated, as they enable critical communication, drive technological advancements in warfare, and support operational effectiveness. Ensuring the reliability and security is vital for maintaining functionality and superiority of military forces. Now, to explain a little bit more this initial setup, we have a wonderful panel of 3 panelists. And first we have Dr. Roland Meier, is a scientific project manager at the cyber defense campus of Armasuisse in Switzerland. His main research interests are security of computer networks and network programmability. Prior to joining Armasuisse, Roland obtained his doctoral degree from ETH in Zurich in 2022. Welcome, Roland. Next to Roland, we have Silke Holtmanns. Silke holds a PhD in mathematics and certified information system security professional and works in a telecommunication security expert in Finland. She has been securing mobile communications since 2000. She represented major mobile equipment network vendors many years in 3GPP and GSMA. Her security research was published at conferences like DEF CON and Black Hat. She's a member of the European Union Agents for Cybersecurity Advisory Group, and her goal is to make mobile networks secure and resilient. And next to Silke, we have Pēteris Paikens, and he is a machine learning and computer security researcher, working as a senior researcher at the University of Latvia Institute of Mathematics and Computer Science, an associate professor at the University of Latvia Faculty of Computing, where he teaches courses on applied machine learning and computer security. So, without further ado, I would like to give the floor to Roland, who is going to explain us on building secure wide area networks over public internet service providers.
Thank you. It's my pleasure to present this project here. As you can see, it's joint work with many colleagues from ETH and from Armasuisse Cyber Defense Campus. Wide area networks, these are networks that connect multiple sites of an organization, for example, different data centers, office locations, university campus, over potentially large geographical distances. These networks, they are important for the organization because they ensure that their different branches or sites can communicate, and they also often carry sensitive traffic and large volumes of traffic. This makes their security a primary concern. Now, traditionally, the way these networks are built, especially for more security-sensitive organizations, is by using dedicated infrastructure, so literally putting their own fibers into the ground in order to have an infrastructure, a network that is independent from the normal internet that we all use in our everyday lives. This indeed brings some advantages for security and for independence from whatever happens in the normal internet, but the problem is that this comes at a very high price tag. As you can imagine, installing all these dedicated connections is very expensive. So for our project, we were looking at the question of whether or how we can build secure wide area networks using shared infrastructure. Shared infrastructure meaning the infrastructure that is provided by internet service providers and that we also use for browsing the internet or for accessing other resources online. The first important question here is, what do we actually mean by secure? And for that, as you probably, many of you are familiar with the so-called CIA triad. It has nothing to do with the intelligence service, and it stands instead for confidentiality, integrity, and availability as the three most important properties that a secure system, including a secure communication system, should achieve. Confidentiality means that the data that is transmitted should be confidential to the sender and receiver, so an unauthorized third party or an attacker should not be able to eavesdrop on that communication or to understand what is the content of the communication. Integrity means that for an attacker, it should not be possible to modify data that is being transmitted, or at least that the receiver of the data should be able to determine whether the data was modified or not. And finally, availability means that the system should remain available despite the fact that there might be attacks like denial of service attacks. Ideally, of course, you want to have your system here in the middle, achieving all these three properties. In practice, this is very difficult or impossible to score perfectly on all three properties, but at least it's a good target to have. If we look at it a bit more closely, we can identify some more concrete threats against these three properties. For the confidentiality, these threats are mostly related to eavesdropping. Eavesdropping can happen for payloads, so that would be if the web browsing traffic is not encrypted, an eavesdropper can see which website you're visiting, what the content of the website is, the video that you're watching, the text in the email that you're sending, and so on. And this is today mostly encrypted, but what is still usually not encrypted is the so-called metadata. And that includes things like the source and destination addresses, which reveals who is communicating with whom, or other metadata such as timing information or volume information that tells you or that tells an eavesdropper how much volume is being exchanged between two endpoints. And depending on the network, especially for military networks, it might already reveal too much information if an adversary can tell whether something is going on in the network or not. And the third threat here is related to traffic hijacking, which means that an attacker, by injecting some bogus messages into the control plane of a network, can attract traffic that it should normally not be able to attract. We will see an example of that afterwards. If we look at the integrity-related threats, we have two things that the attacker can do actively. An attacker can inject traffic in order to inject some wrong control messages, for example, for an industrial system, or the attacker can modify traffic such that maybe the message that was transmitted is no longer the one that the user wanted to transmit, or the destination that gets the traffic is no longer the one that was intended. And in the final group of threats, we have those related to availability. Here it's mostly related to various types of denial of service attacks. If the attacker is having access directly to the communication on the link, then he or she can just drop all the traffic. This is a very simple attack against availability. It's also possible to, again, do these hijacking attacks that I mentioned before. Another problem for availability is congestion. This occurs when there is a high load on a network infrastructure. It doesn't necessarily need to come with malicious intent. It can also be just that many users are active or are transmitting large volumes of data. Something similar happens in volumetric denial of service attacks, but there the malicious intent exists such that the volume is on purpose created in order to introduce congestion or overload on some systems. And the last threat would be related to topology changes. If, for example, a router fails, it takes some time until the network converges to a new state, and during that time, some parts of the traffic might be lost, or the communication is not available for the endpoints. So these were the most important threats that such a secure wide area network should be able to provide. And in the next few minutes, in the remaining of my talk, I will go more into the details of what components in terms of systems that are needed to achieve these properties on shared infrastructure. I will summarize what the current status of these components is, what is already available and what maybe not. And then I will present you 2 use cases where such an architecture can be used or was already used. So let's look at the components, and for that I go back to the list that I introduced before and now add another dimension of the mitigations. Now, one of the first things that comes to mind for protecting network traffic would be to add encryption, and this indeed helps at least for protecting the payloads. It also helps a bit for the metadata, for some kinds of metadata, and depending on what kind of encryption is used. But the problem with most encryption schemes is that they hide the contents of network packets about as well as this packaging hides its contents. The details are no longer visible, but you might still be able to guess what is inside. While on the other side, what we would like to have is more something like this that reveals much less about what could be the content of a package or of communication. And in order to achieve that, we need another mitigation technique that is called traffic shaping and padding. And this works by adding more bytes to network communication in order to hide the actual size of the transmitted data and to reshape traffic such that it follows a constant or predefined pattern that doesn't change no matter how much real activity is going on in the network. Here you also see that this mitigation can have a negative impact on the congestion property here in the table. That's because since we are adding more data, the amount of traffic that is being transmitted in the network increases, and this could, if it goes wrong, could lead to more congestion. And then the next problem that we should consider is this, what I mentioned as traffic hijacking before. Here the problem is essentially that if we have this network that I used in the beginning, and now we have this adversary on somewhere in this fake island that basically says, hello everyone, so I'm here, please send me all your traffic and I can afterwards forward it for you. That's a simplified illustration, but it's quite close to how the internet today works, where each of the individual networks announces the network prefixes, the IP ranges that it can accept traffic for. And then as a sender network, you would decide where to send your traffic based on these advertisements that are being received from all the other networks. And if another network is not performing in a benign way, it can also advertise prefixes that it doesn't really own or cannot really forward traffic for. And in that example here, this would lead to the situation where some parts of the traffic would now be sent to this attacker, and the attacker can forward it to the destination or just drop it, depending on the intentions. These kinds of incidents actually happen more often than one might think. In many cases, it's more because of mistakes, because network operators make mistakes in configuring their routers, but there are also instances where these kind of occurrences happen with malicious intent, such as this example here. And the solution, again, for that problem is to have a way to control where the traffic is going without trusting all of the networks that are processing the traffic at some point in the internet. And this is what is called path control. And as you can see, it solves or it addresses a lot of the threats that we identified before. Then the next thing that this attacker could do is that she could also inject traffic either for denial of service attacks or for other purposes. And here the solution is are many different systems that allow to filter traffic based on the source, maybe only to only accept traffic from trusted sources, or based on the application, based on any other properties. Then there is authentication of the path that the traffic took, and also of the traffic itself, like that the sender is authenticated. And there should be prioritization such that in an event when there is maybe natural occurrence of congestion, only the important traffic is being sent. And also in the case when it's not possible to distinguish between denial of service traffic and normal traffic, that the traffic that looks more normal should at least get higher priority. So that's now our set of mitigations that we should have. And again, the next question now is, now that we want to have all these properties, now we need systems that can provide them. And we start with IPsec, or actually many other VPN techniques provide similar properties that would address at least the encryption part. So with that, we can have encrypted tunnels. Metadata is not perfectly protected, but at least payloads can be protected like this. And then for the path control related topics, we need a bigger change to the way today's internet works. And the solution that we suggest for that is an architecture called CyCon. CyCon, that stands for Scalability, Control, and Isolation on Next Generation Networks. And it's basically a new internet architecture that could replace the BGP-based architecture that is mostly used today. CyCon started as a research prototype. I will show you that afterwards. And the biggest difference between the way how today's internet works and how CyCon works is if you have the host here somewhere in the US that wants to send a network packet to Estonia. With today's internet, the host would send this packet and basically encode in the packet that this packet should go to Estonia, like in the IP address. And then here in that example, all the networks in between would take care of that the traffic takes the right path towards Estonia. And usually the right path means the one that is the cheapest for the networks that are involved. With CyCon, it's different. Then there, the host would not just say where the traffic should go to, but it would also say the exact path that it should take. I put here all the flags of the countries along this imaginary path. In reality, it would not be countries, but it would be the IDs of the networks that should be traversed. And as I mentioned, CyCon, it started as a research system more than 10 years ago. In 2011 was the first publication. Since then, there have been many more publications. The development is by large extent driven by a research group at ETH Zurich. And besides the research efforts, there has been also activities on the commercial side. There has been a spin-off company from ETH that is commercializing this CyCon connectivity. And in the meantime, also many internet service providers are offering this CyCon connectivity as a service. These 3 examples here are Swiss ISPs, but there are many more internationally, also in Estonia. And once we have CyCon, this doesn't just address the path control topic here, but it also enables additional extensions. And these next 3 rows here, Lightning Filter, Fabrid, and Helia, these are systems that are based on the CyCon architecture, but add more properties that fill the holes in other parts in the table that we have here. And then for the remaining 2 components, we should consider that for some parts of the traffic, performance is more important than others. Like for some, it's very important that the defense system can run at the line rate of the network. For example, to mitigate denial of service attacks, they sometimes run at terabits per second. You need to have a system that can process these terabits of traffic per second. And similarly, for the traffic shaping and padding, you want to have something that can respond very quickly to changing network loads in order to reduce the overhead that is added. And for that, we add two other systems that are based on so-called programmable data planes. The systems are called ACC Turbo and Ditto. And these two systems can provide protection against denial of service attacks and against traffic analysis attacks at very high performance. So now that we have at least one solution for every mitigation, or one technology that addresses every mitigation here, we can look at what do we need, what is left to do if we now want to have such a network based on these technologies. And for that, we can look at the technology readiness level and whether these technologies are already available or offered from the internet service providers. For IPsec, this is quite clear. This is widely used for many years, and everybody can just set it up. There is no need from an ISP to have an ISP supporting it. CyCon, I mentioned before, is already supported by several internet service providers, and it's also in some environments used for productive applications, but not all of the ISPs, of course, support it. And then there is this large group of extensions to CyCon or to programmable data planes that are implemented, but only as part of a research paper. So these systems, they are not production ready yet, and this would be the main challenge for the future, to bring also these systems to a state where they are first implemented in a way that is production ready, and second, supported by internet service providers. At the Cyber Defense Campus, where I work, we are looking at this in a lot of detail, and we also try to push this development of a secure wide area network architecture. And as part of these efforts, we have at our 3 sites, we have offices in 3 cities in Switzerland. We have set up a CyCon-enabled router. We have connected these 3 sites to the CyCon network using 3 different internet service providers, and so that we now have a small test bed of parts of the architecture that I was presenting here. All the parts that are commercially available are also running in our test bed. And last year, we also added connectivity here in Tallinn to have this international component as well. So that's our small test deployment right now with a CyCon-enabled wide area network. This has been used for a lot of research projects already. One example that is not really a research project, but is more a practical use, was recently in the Lock Shields exercise that was taking place in April. There, as you probably know, Lock Shields is the large cyber defense exercise organized by the CCD-COE. The red team, the attackers, all the infrastructure, all the organizers are based here in Tallinn, in that very same room actually. And the blue teams, the defenders, which are the main training audience, they connect to the GameNet infrastructure remotely over VPN connections from their home countries. And for the Swiss team, we worked together with them so that they had 3 different ways of connecting to the GameNet infrastructure here in Estonia. One was traditionally over the internet, one was as a backup over Starlink, and the third one was also over the CyCon network, such that we could gain first experiences in that. And then the second use case, this is more of an idea for in the future. If you have an organization like NATO that has some member countries that are put here in blue and some other countries that are not members, and now you want to set up a wide area network that connects infrastructure distributed over some of these countries. An architecture like the one we propose would be very beneficial because, of course, having these dedicated connections over multiple countries is extremely expensive, while what this architecture can achieve is much cheaper. And so that in the end, for all the sites that are connected by member countries, the architecture would directly allow to make sure that traffic only flows over networks that are in these other member countries. And even if it's not possible to have this connection, like in the example here on the left, then it's still at least possible to select to which other non-member countries the traffic should go, or maybe to take additional protective measures to protect this tunnel between the two closest member countries, or maybe to do this part over a dedicated link or something else. So that would be our main vision for how such an architecture could be used. And with that, I'm now coming to the end of my presentation. I hope I could show you that wide area networks can be built in a secure way using the shared infrastructure of ISPs. The main challenge to get there is to make some of the systems that are already designed, already have prototypes implementation, to make them ready for production use. Thank you for your attention.
Thank you, Roland, for this wonderful presentation. I would like the audience to keep all your questions at the end. We've foreseen 20 minutes at the end for the 3 different speakers. So our next one I would like to come to the stage is Silke. Please, the floor is yours.
Thanks a lot. So I'm going to take you to the world of 5G. And this is joint work with Bruno. And actually how this happened might be interesting backstory. So I was the opponent for Bruno in his PhD thesis on 5G slicing. He works for Telenor and is also involved in defense projects. So, and after the thesis, we sat down over a nice glass of wine and were discussing, okay, if you use 5G for defense, yeah, this should be in place, and yeah, that should be in place, and yeah, that's also important. And then we sort of, our napkin got fuller and fuller. And then at some point of time, we decided, let's write it up properly. And let's give it to the people who can really use it to help you sort of identifying secure 5G. So my background is in industrial research, so that means I have not the luxury of an academic saying sort of, you should fix this or that, sort of, I also need to sort of deliver the answers. So let's start with 5G technologies. 5G technology is a disruptive enabler. So NATO considers 5G as a priority area. The NATO Communication Information Agency has identified key areas for 5G in defense, like communication information system, tactical operations, maritime, and static communications. 5G has a lot of features. It's amazing. So you can do a lot of things with it. And the main point of 5G is that you can customize it to your needs. With 4G, that wasn't so well possible. With 5G, you need big bandwidth, here it is. You need low latencies, yeah, that's your choice. You have a lot of IoT devices, okay, here, that's a possibility. So it can be customized for your use case. That's much, much different than 4G. 4G was a sort of all-purpose tool. So, and also in relation to defense, 5G, there's a strong interest to be used by defense for various purposes. So I want to help you getting the best out of that tool and to get it out in the most secure way. So let's have a look at the usage. So this is basically based on a report that was done here by the CCDOE on report on 5G risk for military movements. And they were studying basically, okay, we have now a joint operation, and what happens there? You put this equipment on a ship. You have their maritime communication between the ships, and you might use satellite. So you ship the stuff to the harbor, Rotterdam or Amsterdam or wherever you are going, and there you have private networks. So your equipment might use these private networks in the harbor. What's next? Then you put the things on the rail or on the road, so you're using public networks. I suppose if you land in Rotterdam and you want to go somewhere east, you will cross a border or two, so this means roaming will be involved. So it's not automatically sort of just one country or one network you will be using. You will be using several networks, public networks. And then you land at the place of deployment, where you might have soldier-to-soldier communication, and you might then have a local headquarter where you communicate with, and this local headquarter might then communicate back and use applications at home. So this means we have a lot of different kind of networks there, and the security requirements depend on the intended usage. I didn't even discuss cases like border drones, which is currently very popular in Finland. The discussion sort of should be used drones to ensure the border security. Those drones obviously would need high availability and also sort of bandwidth to transfer video information. Soldier-to-soldier health, I mean, it's sort of indicated there. That's also, for example, very important in Latvia right now. So there are many use cases, and each use case is somewhat different. So, but let's take one step back. Everybody should learn something from this presentation, and I hope you learn at least something now. You will have there bubble paper, Coca-Cola, gin tonic, hope you don't have headache from yesterday, Facebook, and Viagra. And one thing that's the same for all of them, they were designed for something completely different than we use them today. Really, absolutely completely different. So how many people are aware of what this stuff was invented for? Some people aware of what actually the idea was when the guys invented these things? Ah, there's at least somebody.
Coca-Cola against headache.
Yeah, so Coca-Cola was invented sort of against headache from a morphine addict. So, great. So,
Like a Viagra for heart.
yeah. Heart pain, yeah, heart medicine. So Viagra was invented for heart medicine, and bubble paper was invented as a three-dimensional wallpaper. Facebook was invented to rate chicks on a campus. Sort of, let's not talk about the privacy of that one. And then gin tonic was invented or came up with for malaria problems. So when I said sort of all these, let's not talk about chainsaw. It was not invented for cutting wood. So you see, there's a duality in technology, and 5G is no exception there. So when I designed part of 5G, I designed part of 4G, so everybody of you has something I designed in their pocket. So I didn't design it for defense. So the security requirements I had when I designed the stuff were not for defense. So, and Open RAN is a very nice example of such. Open RAN, so I try to minimize the amount of abbreviation. Open RAN means that the antenna and some pieces of software that doing magic to make the network work. So, and Open RAN means you can sort of chunk the software in little pieces. So Open RAN is something pretty new, and the background is it was not invented because of military or defense or anything else, but it was designed because there was a lack of vendor, basically, because if you throw out the red vendors, let's call them that way, you're left basically with 2, maybe 3 vendors, and as everybody said, okay, that's not really a good choice, so we need more vendors, let's come up with this thing, and we have more choice. So, but now we see that Open RAN is really used quite a lot by defense for usually local networks. And let me put it that way, there is still a lot to do there in terms of security. So that's really a prime example for this was not designed for military. But on the other hand, we see quite clear also in the morning session that defense will have cooperations with public operators. You will buy commercial off-the-shelf equipment. And one thing that might be important to understand, 5G uses IT technology. It uses the same technology that everybody's using. It uses cloud, it uses APIs. So the stuff that when you do Amazon shopping, the same API types are used also for 5G. And you know what? Attackers know IT and cloud. In the past, we got away with telecommunication vulnerabilities for years, but these times are over. So we cannot expect that we can get away with telecommunication vulnerabilities for years. We talk more about weeks. So now you say, sort of, okay, was a really good idea. It's a new technology, and like with every new technology, it's a good idea not to jump head first into it, but to use your brain. So I'm going to show you now how you can structure your requirements to use 5G in a secure manner for your purposes, whatever your purpose is, if you want to have soldier-to-soldier communication or drones or whatever. So first thing, it's a bit like cooking. So you need to understand what's your recipe, what you wanted to do, and then you start creating a shopping list. It's basically the same, a bit, maybe slightly different. But yeah, well, it's not so, or creating a cocktail if you like that more. So we need to first identify what are your security challenges for your usages, and you need to do that with your partners, because in a joint operation we saw there are many partners. And so then you need to have concrete key performance indicators, and they need to go in a contract. And why do you say, sort of, do we need it? Shouldn't just be secure? Let me tell you something. I've been working for mobile network vendors, and if there's not a clear customer requirement with a dollar or euro sign, why should they do it? I mean, there's no incentive for them. So why they cannot tell their shareholders, we invested 2 million in this, and they're asking, oh, how much more did you sell? Oh, nothing more. That's not going to work. So you have to put clear, measurable KPIs so that everybody knows this has to be done, and if it's not done, there's no money. Then there's a clear incentive to do things. So let's do things together. So, divide and conquer. Priorities. What are your priorities in terms of, we already saw the CIA there before, we go to that back. What kind of devices are you using? What kind of networks do you expect to be using? So these are basically the boxes you have to think of. And let's go into the first box. Priorities. What is most important for you? What is the thing where you're saying, in my use case, if I don't have it, I don't do it? If you want to steer a rocket, then latency is absolutely important. Because if you are not in time at the rocket, you cannot steer it properly, it doesn't work. If you have video surveillance, bandwidth, if you cannot see a proper picture, what worth is the picture? So safety, maybe. You want to prevent absolutely that your soldiers are tracked, because then they might be killed. So you have to think about what are the important things for you. What is the most important things? And based on that, you identify your no-go, and then you also know where you might be able to, let's say, compromise a bit, or sort of going down a bit. Next step is, after you know basically what you want, or what you need, what are the devices? Because not every 5G device is able to do the same. You will have devices that won't have 5G at all, maybe just Wi-Fi. What are the devices of your partners, of your cooperation partners? Are they enabled 5G? Do they support slicing? Check it. So you need to have an understanding, basically, what is the equipment doing? So what can it do? And from commercial devices, you also need to understand what to expect from them. So basically, sort of what kind of hardware you have in your cupboard. Then we come to the networks. So networks, which means public networks, and what do you expect them to use for? Do you just have one site and you have a local network, no interconnection, nothing else? Do you want to have internet connection? Think also of the future. You might want to change that at some point of time. Do you want a public operator using that one, with or without slicing? Or do you just want to be a normal subscription in the network? Might be okay for some use cases. Do you want to have a site coverage, and then when the persons move out of the site, then they can use the public operator to have more coverage so that they are always connected? Do you want to satellite? We also discussed here now the basically roaming or things like that for joint operations. So what kind of security requirements do you expect for the roaming case? What kind of cloud partners is okay? Is public cloud okay for some stuff? Or do you expect cloud on site? And what are the things you expect from the cloud to do? So, and when you think about these things, they help you identify who is the best partner for you. Not just some old buddy that you know for ages, but really who is the security best partner for you for networks. So, and here are some sort of KPIs. You don't need to remember them. You have all the books. It's just a sort of teaser, basically, sort of what might the KPI look like? So you can say sort of, okay, what kind of technology you support? How do you isolate slices? Well, how do you deal with legacy? These are all things where you can ask, okay, what kind of API security? So it's also about supply chain security. We didn't discuss that. So how does the operator deal with their vendors? How is the software developed? Do they take open source? Do they actually know what's in their software? That's a good question. I think there's also another talk today on software bill of material. So these things are important because if you don't know what's in your software, then you don't know if you are vulnerable. So these kind of KPIs can serve as an example to create a contract with measurable security. Because if it's not measurable, you cannot expect proper security. Then if you decide to buy network equipment directly and run it yourself, then there are other options. So one typical option is you buy from, let's say, Ericsson, Nokia, Enea, Mavenir, whoever, and then you say, okay, it should be at least roughly tested. So I would suggest you say you want to discuss, which means it's sort of, okay, it's some basic level of security, but there are things which don't have these kind of things, so routers or switches. So for those, you need other things. Also, you might want to see, okay, do you have some pen testing report? Because if they test the things themselves, yeah, you might say, yeah, you tested it yourself. Show me reports, some third neutral party who has tested the stuff, so that you really know, see the reports and see how vulnerable the things is. Remember, these are telecommunication companies. They have they know how to do radio networks, but they are not IT security companies. So it's good to trust, but it's better to verify. So that's my suggestion. And pen testing, be careful, there are pen testing companies out there which might not be so trustworthy. Then we have notification of incidents with vendors. If you have, let's say, a vendor whose development environment is compromised, we saw in the past these kind of incidents, that basically the software development environment was compromised, and by that some malware was inserted into the software. So you want to know if your vendor, your supplier, is compromised. So you want to have that information from them. Same about vulnerabilities. You want to know what is vulnerability, what are expected impacts, and when do I see a patch? So not 2 years to go, so something, but something sort of pretty soon. So, and these things you can put in a contract, and then they are measurable. And then there's also an incentive for vendors to support it. Support of expected lifetime. Vendors usually have in mind, they want to sell you the newest equipment, that's their job, of course. But you might have a different expectation of the lifetime of your equipment. So you need to make sure that patches and spare parts and this kind of support goes along with the expected lifetime that you have. And that should be in the contract. So not that you are suddenly in 5 years, oh, that product has been discontinued. Okay, I just have to scrap it. So because I don't get any patches any longer, it becomes insecure. So these are things that you need to consider and think about when you do these kind of contracts and procurements. So basically, it's about creating lists. So latest till Game of Thrones, I think everybody knows that lists are important. And it's important to align those lists with your joint partner. So again, priorities. What's the most important things for your use case? What's the thing that your use case can absolutely, if it doesn't have it, it doesn't make sense? What are the devices you expect to use? What are your expectations on the networks, like routing, roaming, support, and so on? So then really having a list of concrete security APIs which allow explicit measuring if something is done or not done. And also you have then the proof, and not just some slide saying, I'm secure, this is the security you are looking for. So this is basically what you need to remember, these 4 things. So, and if you don't do this, I can guarantee you that you will not get the security you would like to have. So you can either do it yourself, based on the paper. There's a lot of more details there in the paper, sort of which can help. I just was a teaser here on the KPIs. Or you can sort of get some expert on this sort of. The choice is yours. But I hope to help you somewhat on the way of creating a secure shopping list for 5G. And sad truth is, if you don't do that, you will probably less secure equipment than you want, less secure services, and it will have an impact on your usage. And I cannot then guarantee for 5G security usage. Thanks a lot. I hope you enjoyed the talk and looking forward to questions afterwards.
Thank you, Silke. Last one, but not least, Dr. Pēteris Paikens, with this paper, Resilience and Vulnerability of Consumer Wireless Devices to Cyber Attacks. The floor is yours.
Okay, hello everyone. So I'll be presenting our research together with Christian Nessenbergs from another institute on what we observe when looking into wireless protocols for consumer devices. So the motivation for the study was actually driven by, how to say, a need to comment on other work which we're doing on identifying vulnerabilities like the protocols for fuzzing, the protocols for exploits, and attempting to, how to say, violate the privacy of devices by making methods to identify and fingerprint them. So we needed like an overview of what's happening in this domain, and we didn't have such a study available in literature, so we tried to analyze it ourselves. And I'll take a look at what are the, from theoretical part, the potential threats and motivations of threat actors in this domain. Then I'll summarize a survey of vulnerabilities from last year, which is more detailed in paper. And the interesting part, at least from my perspective, is what is the differences between our expectations and the survey's results, because experience is what you get when you don't get what you expect. So let's move on. So which devices am I talking about? So consumer Internet of Things wireless devices. Those are all the things around you other than the mainly discussed devices like laptops and smartphones. They all are actually very powerful computers nowadays, but since they don't look like computers, people ignore the fact that they are computers and have all the same baggage as well. So there are things on your body, like various headsets, smartwatches, all kinds of fancy electronics that people sometimes use for short term as like a fad, but also devices in your home around you, which again are capable computers, perhaps in your washing machine or fridge in some cases. Home automation is a very, how to say, security intensive area of devices. And those devices have widespread use of wireless communication. So many of them do have widespread use of ordinary wired networks, but we are not focusing that for. We look at the wireless protocols. The dominant protocol in this case is Bluetooth, both classic and Bluetooth Low Energy, which are quite different protocols despite sharing the name. A bit of mainstay protocols for computer networking like Wi-Fi, and sometimes we now see communication done directly with cellular operators like 4G, 5G, and so on. And many, many specialized protocols, like for every, how to say, specific domain where we don't want to use like one of the main protocols for some practical limitation, people have developed specific protocols. So this is the topic of this talk. So what are the risk factors? Why do we think that it's valuable to look at the security of those devices? And the main factor is that they have interesting sensors. If they were just computers, we wouldn't care much because they don't really, how to say, compute much. But they have ways observing things that the users might not want everyone in the world to see. So if I am wearing a wireless headset while I'm on a phone call, the headset has all the contents of my phone call. If someone wants to eavesdrop on my phone, they don't necessarily need to compromise my phone. If they can compromise my headset, they have all my phone calls because they happen on that device as well. And all the things in your home, like if you have a vacuum cleaner that drives around your home, it navigates by cameras, so it films everything in your home. Perhaps you don't want everyone in the world to see what your vacuum cleaner sees. And so it's growing on for more and more devices where we don't even notice or care about the capabilities they have, because, the advert in the store will say, oh, it does this magical thing, and it does not go into detail because of how it does that thing, because it can see or hear you all the time. So we consider these are interesting objects to study from perspective of security. Also, smartwatches are a great example because you may have security of other systems compromised by the fact that you get like two-factor authentication by codes that get sent to you over the phone network, but then that same code gets displayed on your wrist, which again is a different device, which may be less secure than your phone. And of course, there are a bunch of threat actors which have demonstrated an interest into looking at people. And the two main groups of threat actors we see here are very different capabilities. One is espionage by state-sponsored actors, and the other is, private motivation, domestic abuse, and, conflicts between ex-partners have sadly been a widespread case of technology abuse for home automation and in this domain. So what matters here? What is the difference between these devices and ordinary computers? We believe, and research confirms, that they tend to be easier to attack than current modern computers and smartphones, not because perhaps of inherent limitations, but for, historical reasons. They are slightly lagging behind as an industry compared to industry of developing application software. There's still widespread use of C and C++. There are embedded operating systems which explicitly and intentionally don't have many features of modern operating systems which make exploits harder. And more importantly, there's a bigger gap between the buyer and the developer, so there's less motivation for security. So if you get a piece of software from Microsoft and then have a security problem, then there's, a direct link, it affects you. But if there's a security problem in a chip that the firmware was sold to another company who made the device, and another company integrated the device, and then there's 10 vendors in between, which result in actual appliance that you get. There's no link between the software problem and the buyer. The buyers don't appreciate the security of the devices because it's not visible to them in any way. And many of these systems simply can't be patched. Like, my smartphone gets security updates, I don't know how frequently, too frequently for my convenience. Well, my headphones, I think it's impossible for them to get the security updates. There's simply not any protocol how they could get that information without me bringing them to some service center. So, not happening. On the other hand, these are devices which are much harder to exploit because if we look at wireless protocols, these are all relatively short-range protocols. Even the long-range wireless protocols are still short-range in the global scale. I can't be attacked by a person from North Korea over any wireless protocol. They simply can't reach me without coming at least near this building. So that's a major limitation. Not only because of the distance problem, but also a scale problem. Someone who exploits, I don't know, Microsoft Exchange server can exploit all the Exchange servers in the world. Someone who finds an exploit in a popular wireless device, they can't reach every user of the device in the world without traveling everywhere all at once. And this also creates a risk to the attacker. So if someone wants to perform an exploit and they could come near me, that still exposes them. So there's some physical evidence, perhaps from surveillance cameras, that, hey, this person was here, and they might fear getting caught, and that acts as a deterrent. So what have we seen in practice for all these high potential attacks? We've seen a lot of industry reports about how IoT devices IoT attacks grow by so many % each year, and all of these attacks are like boring attacks by these some smart light bulbs being part of distributed denial of service attacks. And we have had certain cases reported of, again, domestic abuse by surveillance by ex-partners, like very few such cases. And that's it. So we expected to see something more. We took a serious look and didn't find it. So none of these attacks actually rely on exploiting wireless vulnerabilities. The people who make distributed denial of service networks, they obviously need devices which are reached by internet connection, and they can exploit millions of devices at scale. So we did a survey of reported vulnerabilities. So we don't see exploits in the wild. What do we see in the CVE reports, which people are saying, hey, we found this problem, we found this vulnerability. So we took a look at all the reports we could find from arbitrary choice of last year, like searched some keywords, find out like more than 200 vulnerability reports, which we looked at. And then we did some filtering because many of them, how to say, have the keyword, but they are not specific to this scope of this talk. So we excluded problems with Wi-Fi routers, which are effectively standard commercial network appliances. We excluded problems in Windows drivers and so on. But we did include Android because Android is not used only in smartphones, but many of these interesting smart home devices use Android in their backend. So in total, 163 vulnerabilities, which we considered relevant. And what do we see in these vulnerabilities? We still see that outside of Android ecosystem, almost all of the bugs, exploitable bugs, are still caused by memory safety. So this is where we were, I don't know, 10 or 20 years ago in application software. So right here, this is still the current problem. So, okay, I mean, it's not surprising. This is what we expected to see, but we confirm this with the study. And if we look at potential impact of those vulnerabilities, again, many of them are not as interesting to the attacker, like there's some information disclosure, there are some vulnerabilities which crash the device, which isn't that relevant for most of these appliances. You crash them, they restart. If you can deny their attack, perhaps you can make an inconvenience for someone. But there's still a meaningful proportion of vulnerabilities which do grant effectively full device takeover, like 25% or so. So if the attacker wants to take over a device, there exist vulnerabilities. And these vulnerabilities, how to say, were not very sophisticated vulnerabilities. Like if we compare the CVEs reported for exploiting a Bluetooth device and CVEs reported for exploiting a modern browser, like there's a world of difference. The mitigations you have to circumvent for modern attacks are, how to say, quite serious, and these are basic low-hanging fruit in many cases, like obviously low-hanging fruit. And still, none of these device takeover vulnerabilities had asserted that they have seen exploited them in the wild. So there's this big gap. We did not find what we expected to find. We expected to find, okay, there's a motivation, the vulnerabilities are findable. It doesn't seem that they were difficult to find. The methods of identifying these vulnerabilities, as described in the reports, were straightforward. The exploitation was, again, reasonable. There are proof of concepts. These are not complicated proof of concepts codes. The impact is there. They would allow to do surveillance on someone without their knowledge. Motivation seems to be there, but we don't see any attack. So how come? So this is a study that raises more questions than answers. So now we're moving on from the study to guessing. My hypothesis for this, one option is that could be valid was that there's a lack of motivation. So we had some ideas about motivations, perhaps my ideas are wrong. So if we look at general what motivates people, big three things, money, sex, and power, we do see that these are not motivated by money because they are hard to monetize, unlike ransomware and so on. Requirement for physical proximity makes it difficult because criminals who want money, they also want to spend that money not being in jail, so they prefer to attack people in a different country, far away. So it's also a big impact. We do see it used in domestic abuse cases, but they don't need exploits. They have physical control of the device, they have credentials, and if they want to harm their ex-partner or potential partner, they do it without cybersecurity skills by applying physical control. And for political power, intelligence actions would seem to have a use for this, but how to say, it's not documented. We assume that there could be motivation for them because the exploits for these wireless devices seem to be simpler and easier than exploiting a modern smartphone, which have improved in security greatly in the last few years. So hypothesis number 2, why we're not seeing these attacks, is lack of capability. So again, maybe financially motivated attackers would have the capability to make these exploits or hire someone to make these exploits if they found a way to monetize it. But as we saw in previous slides, there isn't a good way, or at least doesn't seem to be. Personally motivated attackers would have limited capability, but the intelligence agencies trying to do targeted surveillance, they definitely have that ability. We have seen very sophisticated smartphone exploits like Pegasus, TriangleDB, and in comparison to those, making a very hard to detect exploit for, again, some wireless headphones or keyboard would be simpler than the ones we have seen them make. So they definitely, if they can do those smartphone things, they can do simpler things as well. So hypothesis number 3 is that maybe there are exploits, but I'm just not seeing them. So it could be that attacks are very rare and targeted to very few people, which seems a reasonable assumption, but again, can't get any evidence for that. Or perhaps we are unable to detect such attacks because, again, I've spent quite some time on analyzing these like wireless vulnerabilities, and if my own headphones were compromised, I'm not sure if I would be able to detect that. Like, it would not be a simple thing to verify any suspicions, you know? If I could try to extract the firmware, but if the attack is like living in the memory, then it could not have any impact on the firmware. So they are hard to detect, even if they were. And finally, there's an option that some people detect them but do not tell the general public. Again, who knows? So these are the three hypotheses. I can't say that I have any evidence to prioritize one of them over the other, but I would say that if we look at the state-backed actors, that hypothesis number 1 seems unlikely, and hypothesis 2 seems also unlikely, and perhaps there are things that we can't detect, because according to all this logic, there should be attacks. These are low-hanging fruit. There is a capability, there seems to be motivation, and do we believe that nobody is picking these low-hanging fruit? So that's mostly what we see. Yeah, we see that wearable device security is, how to say, not up to the level of modern smartphones. Perhaps this is something we can fix, just as we fixed modern smartphone security, but I feel there is limited motivation for the vendors to fix that. So I don't expect that to change anytime soon unless something changes with liability or other types of motivation. So another observation, or final observation, is that we should work more on trying to find methods for analyzing such devices so that if there were compromises, that we could more or less reliably say, oh, I looked at this device and it actually looks okay, or it actually is compromised. We can try currently, perhaps some people in this room can do this, but I can't, so I'd like to have published work on how to do that in a reasonable manner. How can we tell if a specific device is compromised or not? So that's my talk. I raised some questions, and that's it. Time for questions. Thank you.
Thank you, Pēteris. So I don't know if anybody from the audience already has a question for one or for all the panelists. I see a person there. 3 in the same area. Yeah.
Hi, this would be a question for you, Roland. I'm interested in the path control you mentioned within CyCon. I understand that once you reach the ISP, which has CyCon router, you can control the path within them. But before you reach such ISP, for instance, if I have my phone and I want to use CyCon from my phone, how can I control the path between the device and the ISP? And if I can control it, what value do we gain by controlling just a portion of the path?
So for the phone, it's maybe a bit special. Normally, so CyCon is a routing architecture on the AS level. So it's an interdomain routing architecture, meaning you route between different networks, like different ISPs or core networks. The path that traffic takes within these networks is not necessarily under your control. There are some extensions that can do this as well, but the goal is mostly to have the control over which networks are traversed. And in that sense, the path between your device and your ISP, since this path is within your ISP, you need to trust this ISP, otherwise you would need to use a different one. So this ISP in that case would always be in the path if it's the only one that you have.
Okay. I saw there was another question there from Mr. there.
Hello, everybody. Elir from Albania National Assert. I will start with a suggestion for Dr. Pēteris that for this hypothesis, I think that the idea that is undetectable is more reasonable because there are cheap devices mostly in the IoT and the people think it's misfunctions, so they throw it away, even that is attacked or not in this case. So, but a question is for you, Dr. Roland. In the case that we use that connection, because I was thinking about the Albanian case, if we can literally say that force the critical infrastructures to be connected via the network in that way, is it really let's say safe that maybe most of the DDoS attacks can be lower in the value in the amount of attacks?
Is your question is about that there can be denial of service attacks in CyCon or? Yes, there can be. The solution for that is that since you have this path selection mechanism, you can also do bandwidth reservation on that path. I didn't cover that in my talk, but you can reserve bandwidth for your communication between your endpoints. And in that case, this path the bandwidth is reserved for you. And so if there is a denial of service attack, it could not affect your bandwidth that has been reserved for you.
Okay. Was another question there, I think, the man in the...
Yep. Casper from Royal Danish Defence College. I have a question for you, Pēteris. It's about medical devices. Are you concerned about the vulnerabilities in testing in medical devices? I've heard some stories about the tests on medical devices, even though they're vulnerable, they don't get pulled back and reapproved because the approval process is so long, so they just don't care about it, the vendors.
Yeah, so we do consider medical devices. We consider them as subset of wearable devices, a very, how to say, important subset of these devices, but we don't really treat them separately because from the perspective of technology and vulnerabilities, they generally use the same components, the same architecture for these wireless communications, but they simply have a larger impact. So one difference is that there is a stronger motivation for these vendors to at least try and build a quality product. But we still, as you say, they don't patch them. It happens. If they have a security problem, does it really result in lower sales for them? Like, would you refuse I don't know, heart stimulator just because the vendor has published vulnerability? You will, if the doctor says get this one, you'll pick that one because it's a better medical device. So yeah, there are risks for medical devices, and we consider that the same vulnerabilities apply. They use the same chips for wireless communications, generally the same firmware, and would have exact same vulnerability as a different device doing different function.
Okay, thank you. Some more questions in the room? Yeah.
Thank you. Hi, this is a question for Roland. Thank you for your interesting talk. How do the measures that you were talking about protecting the networks affect security monitoring? Is security monitoring there in the network affected somehow? Are there the normal devices, IDSs, IPSs, still used, or do they have to be adapted? What's the impact on this security monitoring?
So since we are talking about wide area networks here, this would be the network that connects the different sites of an organization. So everything that happens to your traffic before it leaves your current site of the organization or after it enters the next site is not affected. So any IDS that you have running and that you have to observe the traffic is not affected by this architecture. It's only affecting things that are outside of of your physical location, kind of.
Hello, Urmas from CCDCA. Regarding telecom vendor certification, so is it really like a realistic thing to do? Because, and we know that mainly it is because of Huawei to show themselves as a, I don't know, trustful partner. But in reality, it is that there is, I don't know, like 2 major software upgrades coming like every year, software updates in the middle, and then also all the customization levels, what all the operators are actually requesting and needing. Then is it really like a way forward, or is it?
So what exists there exists this CAS system, which I mentioned, which is basically, it's specified, there are test cases. There's on this level sort of, okay, making sure that there are no hard-coded passwords, that the passwords are sort of changed after the first usage. So there are these kind of specifications that are generic for all nodes, and then there are node-specific. So I think this is basically good security hygiene, and actually the big vendors, they use these certifications. So, and I think when you are setting up a private network for your purpose, you should also have at least this kind of baseline security. With regard to vendors, sort of, it depends on how much money they also want to invest in this kind of security. Then there are equipment where you don't have these kind of test specifications, but you still might want to have it somehow assured that the things are properly set up and configured and so on. So like if you have, for example, voice over LTE or IMS systems and you want to send videos, you still want to ensure that these systems are safe. So, and for those, one way to do it is putting in the contract sort of, okay, do you have a pen testing results of those? Because some of the vendors, they have been pen tested by some governments, which are also in NATO. So you might want to ask them sort of, okay, can we see at least a summary of that report? And what did you do about it? So you can apply a bit of pressure on getting them to see that this is really a value for them if they improve their security. So certification is definitely not a silver bullet, but I see it as part of a stepping stone to ensure that there's at least some baseline security there. Some basic security testing has been done. And I said, but it's not valid for all nodes. Some nodes don't even have this kind of certification possibility at all. So, and I would call it basic testing. So it's not, if you go to the IT world, they will say, yeah, that's clear, you shouldn't do it. You should do it always, sort of. Why do you ask even about it? So, but in telcos, this is something a bit newer. So,
do I see somebody else from the audience who has a question for our panel? At the very back.
Hi, I'm Carlos with CCDCOE. I have a question to Pēteris regarding the small Bluetooth devices and whatnot. I think that basically the more fancy ones come with Android or iOS apps. So I see that that would be a vehicle to push updates to them, but also like on the other hand, like a nice way to communicate back to the attacker so that you don't have to be in the vicinity of the device for all the time, but like just own it once and then keep control forever. Any comments on that? Thank you.
Yeah. So we have seen some exploits for these mobile apps controlling a device. So because again, perhaps they are easier for the attackers to reach and easier for defenders to detect, because this malicious app is now on App Store and publicly visible, unlike firmware of some device. Yeah, I agree with the general concept that there could be a mechanism to push updates. The issue is that there isn't a mechanism built to push updates because all these vendors don't ever want to build updates, because why should they? They have already got your money and they don't intend to support this device in many cases. So they could make such options, but they currently, as a rule, do not. These cheap devices, they are treated as disposable, even they have quite powerful computers within, because currently powerful computers are very cheap. Yeah. So there's no motivation, in my opinion.
I see there's another question from there.
This is an academic question, right? You know, you got the network layer and you have the different protocols. Do you see us expanding from just different networks, different protocol layers to including 5G vendor chips? And if it's going over a certain vendor, it might route differently, right? So if you go back to the routing protocols and says you don't want to go to this network, do you see us expanding from going to the OSI model from a layer 4 to maybe bring it into something from the session layer into some of the routing, whether it's 5G or whether it's just traditional WAN links?
I think you can take part of it and I can
Yeah,
then compliment. Okay, so for example, most of you here will be roaming. So when you set up a call, let's say to home or sort of pull data from home, then it usually works that way that the route where your data flows through the operators are connected with each other through something called interconnection network. That's their sort of own huge private network. And it's not the internet. So, and when you roam here and let's say you browse a website somewhere, this is usually routed via your home operator. The path this takes, it depends on money actually. So because depending on the route, the price for routing is different for the operator. So in telco, the routing path is determined by money. So that's how telco works. And then I give sort of to the technical part of routing, how routing works on the internet. So, a different way.
In today's internet with BGP, it's clearly you cannot influence the route that the packet takes. You only specify the destination. Now with this sign-based architecture, in theory, you can select the path for every packet separately. If you implement the sign stack on your end device, then you can encode which path the packet should take directly in every packet. And this can be, of course, influenced by the application or by the time of day or whatever you want, basically.
I'm basically kind of looking at a Chinese manufacturer of backbone devices, right? And they might be linked to eavesdropping and things like that. So, you know, if that's on the backbone of a certain network, can you kind of, again, it's academic, right? It's like, hey, I know this vendor signature, or I know that doesn't have a patch, right? So I'm going to take something else because it's not patch worthy as it goes through. That's what I'm
Yes, and that actually relates to one of the systems that we have in the list that allows to not just specify the path at the AS level, but also within a network. Because if you want to exclude some vendors or some software versions, or you only want to send traffic over routers that are powered by renewable energies or whatever properties you want, there is one of the extensions that you can do that, so that afterwards your packet will only accept paths that fulfill these criteria to the extent that each of the networks supports it, because the network would need to declare that, of course.
I can say something. So if you actually want to pull off, let's say, a traffic redirection from a user, sort of the way you would do it, you have a big database in all mobile networks where there are things specified like your phone numbers, your device number, the identity of your SIM card. And there also in this big database, it's called subscriber profile, there are sort of also information for routing and sort of how your traffic should be routed to the nodes and sort of if it should be routed to your home network and things like that. And as an attacker, the easiest way, if you are managed to modify this subscriber profile, the easiest thing is just to put there, okay, route the traffic to this node. That's the easiest way to do it. So you don't need to go to the chip level. It's much easier to do it on telecommunication application layer. And yeah, that these kind of things have been done. For example, that's how SMS interception works. And you might have heard about one-time password interception for SMS. That's how these things work. They just change the SMS server address, and then it's sort of, they get it, and then they route it further, and nobody has seen anything. So that's a trick how you do interception in mobile networks. If you wanted to from the back end, so and not from the radio interface.
What are the capabilities to achieve that?
Depends on so in 2G, and it depends really on how well the networks are protected. So if the networks are not well protected, these kind of things have happened. So there have been cases, let's say, that Bitcoin vaults have been emptied because somebody intercepted the SMS passwords. It can be done in 2G, 3G, 4G for sure. In 5G, this is a bit more difficult because actually, I think the attackers still use the old technology and it works fine. So that's why they haven't moved on to 5G in my book. So yeah, but it depends really mostly on signaling firewalls. That are the firewalls that sit on the roaming interface. Because in the roaming network, we don't even have authentication right now. So everybody can do everything, and nobody is smarter.
Just one idea for Dr. Pēteris. Maybe the dynamic application security testing could be used in terms of analyzing the third-party IoT devices, analyzing actually the application that is running, and for the security concerns.
Yeah, we can do some analysis of, how to say, internal states of devices, which we do for fuzzing in order to try to like bring a device to interesting state. And similar technologies can be used also to say like, is this device different from an identical device, supposedly identical device sitting right next to me. The problem is like, it's difficult to get good instrumentation about what's happening inside of such device. And since the device itself is like cheap and disposable and, how to say, we don't want to spend excessive amounts of time to analyze each very cheap purchase. So there's like an economic problem on, is it feasible to verify each such device? Because there's a big variety also of these models. Unlike like laptops where you have a limited number of major manufacturers, you know, for all kinds of consumer devices, like there are a dozen products every day arriving from various vendors.
Then a second question here, for the end-of-life support, should it, from your opinion, just personal opinion, should it be any requirement from the manufacturer to provide any sort of the disclosure of the firmware if they finish supporting, so it can be
That's a very
analyzed?
interesting question.
That's a good idea.
Multiple aspects. So one aspect is there's no end of life for such devices because their how to say their end of life is at time they're sold. They will not get any support ever. But firmware is a tricky issue because many manufacturers have not even been legally able to provide the firmware running on the devices because the way at least many of these devices work, they use licensed IP for certain functions, like especially the wireless communications, which they did not develop themselves, which they licensed from another company who licensed from another company with all the old bugs, and they don't even have the rights themselves to modify or publish key parts of this firmware. And those are the parts of firmware which there actually are these sometimes vulnerabilities in the Bluetooth protocol implementation. So as far as I'm aware, we don't have any good published firmware source code of any like Bluetooth device, which does actual physical layer of Bluetooth. Like we have decompiled binary with questionable legality. So if someone knows source code for Bluetooth implementation, let me know. We would like to have that happen, but again, who's going to force them?
The legislative.
Yeah.
Thanks.
I think we have still time for at least one more question. So if somebody is interested in asking a question, please. Nobody? Okay, I can ask a question myself. Maybe for Roland, can the presented architecture be combined with existing infrastructure? So the dedicated infrastructure or based on today's internet?
Yes, definitely. So with these, it can certainly be combined with the dedicated links. So you can have parts of your wide area network running over the dedicated infrastructure and parts over this architecture that I was presenting. Technically, you can run the infrastructure over tunnels that are using today's internet. The problem then is that with these tunnels, and because the underlying architecture is today's internet with all of the shortcomings, especially regarding path control, you also inherit all of these weaknesses. So that's maybe less advisable. Technically, it would be possible. And combining it with maybe dedicated networks that are for the geographically closer data centers, that's certainly an idea, good idea to do.
Okay, thank you. Still not running out of time, so it's good. Silke, it's already break.
Oh.
Okay, let's break then.
Sorry.
Clock says 2 minutes.
Yeah, please applause for this.